Hello, welcome in the 19th lecture of convective heat transfer. In this lecture, we will be discussing about mass transfer. Mass transfer is quite analogous to whatever we have discussed in the last few lectures, which is heat transfer. So, here we will try to see how convective heat transfer relationships can be used for mass transfer. Okay. So, our topic for this lecture is mass transfer. So, let me first tell you that what outline we are going to follow in this lecture. In this lecture, first we will be introducing what is mass transfer. Okay. Then we will be going for Fick's law derivation. So, we will be deriving the Fick's law and we will state what Fick's law is having. Next, we will be deriving species transport equation and finally give you mixture momentum equation. Okay. So, momentum equation for the overall mixture of different species. Then we will pose the idea of forced and natural convection driven mass transfer. So, here we will be showing you similar to forced and natural convection how forced mass transfer and natural mass transfer can happen. And at the end I will be showing you different mass transfer related non-dimensional numbers and try to establish analogy with the heat transfer. Okay. So, let me go inside. To begin with, first I will be giving you idea of diffusion between two different components. Let us say we are having species A over here as water and species B is some liquid blue dye. Just whenever this dye is entering in water, you will find out that blue color dye is diffusing in water slowly. Okay. Though they are non-reacting mixture, okay, there can be reactions also, but in this case though they are non-reacting mixture, water and liquid blue dye, those are non-reacting mixture, still we can find out diffusion helps in mixing. Okay. So, this type of situation if we start to study, then we can immediately define the concentration of individual species. For example, let us say the concentration of species A in this case is Ca. Let us define the concentration as C. So, concentration of species A is actually Ca. Okay. So, this concentration is nothing but analogous of at a particular location. If you try to find out the density of species A, that will be equivalent to the concentration. So, we write down Ca is nothing but rho A and the concentration will be having same unit kg per meter cube as density is having. Okay. Next, let us see that if we try to get the mass fraction of a species in the mixture. Okay. So, if we try to get the mass fraction, let us define mass fraction in terms of W. So, let us say mass fraction of species A is nothing but WA. So, WA will be nothing but MA, mass of A at a particular location divided by mass of A plus mass of B. So, whole mass between two component mixture. Okay. So, if we do a little bit of division in the denominator and numerator over here by delta V, we can convert these masses into corresponding rho densities. So, density of species A divided by the mixture density rho. Okay. So, we get mass fraction in the form of density fractions rho A by rho. So, if we consider a binary mixture, then definitely we will be finding out that rho A plus rho B is equals to 1. So, that means WA plus WB is equals to 1. That means rho A by rho plus rho B by rho is equals to 1. Okay, where rho is nothing but actually MA plus MB by del V, that means your rho A plus rho B. Okay. So, ultimately this equation for a binary mixture is very much valid and we can say their mass fraction summation is equivalent to 1 for a binary mixture. If we generalize this one for a multi-component mixture, then we will be getting rho is nothing but addition of all the components. So, rho 1 to rho n. Okay, we can write in the form of summation also. and if we try to define mass fraction over here as Wi, so Wi will be just rho I by rho. So, just generalization of this side where we have discussed about binary mixture of liquid, blue dye and water. So, this is the generalization for multi-component fluid. So, Wi will be rho I by rho, okay. And if you proceed further for summation of W, then you will be finding out summation of all the species mass fraction is equivalent to 1, okay. Summation of all W's is equivalent to 1, okay. Just following the same analogy, we can write down this one for multi-component mixture, okay. Let us see now new thing, as we have discussed about diffusion over here. So, one species will be diffusing into another one. So, there will be definitely some diffusivity involved in this, okay, the rate at which the diffusion happens. So, we consider that one as it is mass diffusion, not a heat diffusion. So, let us consider the mass diffusivity of A into B, okay. So, let us write down that diffusivity as D. So, D AB means diffusion of A into B, okay. So, if we try to find out what will be this factor, so we call this one as mass diffusivity, okay. The unit of this one will be meter square per second, okay. So, how much area it is diffusing per unit time, that will be the mass diffusivity, okay. Next, let us see if the length scale of the mixing process is L and the time scale of the diffusion is T, then we can easily write down by matching the dimensions of the mass diffusivity and this L and T, we can easily write down that T will be of the order of L square by DAB, okay, where DAB is nothing but mass diffusivity, okay. So, here from we get that diffusion actually comes due to gradient of concentration. If you are not having concentration gradient somewhere, so let us say here the liquid blue dye is having very high concentration, but here it is low concentration, that is why diffusion will be happening and helping in mixing. So, if you do not have any gradient of concentration, then diffusion will not happen. It is just similar to the heat transfer. If you are not having the temperature difference, heat transfer will not happen. Same case, mass diffusion will not happen if gradient of concentration is no longer there, okay. So, after this, let us see a new law which we will be defining as Fick's law, and this is defined for binary mixture. But before going there, let me show you a small example over here. Let us say we are having silica over here in between two walls, okay. So, this is a silica compact, you can say, okay, having height h, let us say. Now, at the beginning, let us say both the sides of this silica are having contact with air, okay. So, it is having air. So, let us say at the beginning means whenever we have not started the time t less than 0, okay. Then let us say suddenly you keep one side of this silica in contact with helium, okay, another side as usual remains in contact with air. So, in this silica, one side you are having air, another side you are having helium. Suddenly you are keeping one side in contact with helium. Now, silica will be absorbing helium chemically, okay. So, you can find out that slowly but steadily helium concentration will try to increase inside silica, okay. So, after some time, a little bit of time, a small t, you will find out the wall which is attached with the helium, there we are having high concentration of helium. Let us say the concentration of helium is actually Wa. So, the high concentration of helium is over here, okay, and slowly you can find out it is diffusing. So, there is a gradient of concentration, or there is a change of concentration towards the towards the upper wall, where upper wall is in contact with air. Here definitely no helium can reach, okay. So, if you wait for longer time, then you can find out that it will be achieving some steady state, and you will be finding out a gradient of concentration of helium can be observed in this fashion, where once again the bottom wall which is in contact with helium is having higher concentration, and which is attached with the air side, there we are having lower concentration, okay. Now, from here we can at least say that this mass transfer rate inside this silica of helium will be actually varying with respect to obviously z. If z is more, then you will be finding out, or if z or h both are same over here, okay, this is z direction and this is the magnitude of z for this present case, which is h. So, you will be finding out this mass transfer rate will be actually inversely proportional to this z direction or h spacing between the species. Okay. So, if they are very close to each other, then mass transfer rate will be enhancing and reverse will happen whenever they are away from each other. Okay. At the same time, if you see over here, we are having some fixed helium concentration at the beginning, and here helium concentration was 0. So, this helium concentration W A naught, if it increases, then more and more helium can enter. Okay. So, that is from common sense that if the concentration is higher, then obviously it will be giving more push for the helium to enter inside. So, as a result, we can say this m dot or mass transfer for the helium is actually proportional to this W, okay, W A naught, right. So, and definitely this mass transfer rate will be increasing as the area of contact between the silica and helium increases, isn't it, because the contact area increases means more and more area is available for entry of helium. So, with these three things, Fick has proposed that m dot A is actually proportional to W A naught, which is the concentration of helium at the beginning. M dot A is inversely proportional to H, okay, which I have already said over here. If the silica layer is becoming thin, then mass transfer rate will be increasing, as well as m dot A is proportional to AP, which is nothing but the area through which the helium and silicon is keeping contact. So, if you add all these three terms of this equation, then you will be getting m dot A by AP is proportional to W A naught by H. Okay. Here, as I have mentioned, AP is the plate area. If we proceed further, then we can define this m dot A by AP, which is nothing but m dot A is mass flux, m dot A is mass transfer divided by area, which will become actually mass flux. So, this mass flux of A in z direction, this is becoming proportional to W A naught by H. Let us call that term mass flux as J. So, J is the mass flux, let us say. So, J A in the direction of Z is actually becoming proportional to W A naught by H. Okay. Now, as we have found out that this mass flux can be also written in terms of the concentration. So, we can write down this mass flux is nothing but dWA by dZ. Okay. dW by dZ is coming from here. You see, W A naught is actually the subtraction between W A naught minus 0. So, that is the gradient of the concentration which has actually caused this mass transfer. So, we can write down this W A naught as dWA. So, rate of change of concentration in between the layers, and this H can be written as dZ. Okay. So, change in location in the Z direction. So, we have written this JAZ, which is nothing but m dot A by AP from here is equals to is proportional to dWA is coming from here and dZ is coming from H. Okay. So, once we have this type of equation, we can give one constant in the equation also. Let us give that constant as minus rho dAB, okay, minus rho dAB. So, this is the proportionality constant, and this we call as fixed first law. Okay. So, mass flux is actually equals to density into mass diffusivity into dWA by dZ. Okay. This is the concentration gradient. Okay. Next, if we proceed further, then this mass flux can be written as rho A into WA minus W. Okay. So, if you take this component, so here we can write down JA is nothing but rho A into VA minus V, okay, is equals to rho into DAB into del WA. okay. So, rho A into DAB, rho into DAB into del WA, okay. So, here this is nothing but your diffusion velocity, okay. This is nothing but your diffusion velocity at A, okay. So, once you have this one, then we can easily go for conservation of mass. This is mistake, conservation of MASS, conservation of mass for its species or its constituents, okay. So, that if we try to derive now, let us consider that the species A is having velocity VA and species B is having velocity VB, okay. And with this, if you try to get the mixture velocity, so mixture velocity definitely can be written as V equals to rho A VA plus rho VB divided by rho, mixture density rho, okay. So, this equation we get from the mixture bulk velocity V. If you proceed further and try to have a balance of mass transfer, then let us see if mass of species A inside a region R, if we try to find out, then what we need to do, we need to integrate for the whole region, region R. So, volume of the region is V and we are actually finding out rho A into dV, because we know rho into V is actually your mass. So, that we are doing for this arbitrary region R having volume V, okay. So, this is the mass of the species A inside region R. Similarly, if we try to find out net efflux, okay, net efflux of species A from region R, because there will be lots of surfaces. So, from there if we try to find out the net efflux, whatever is coming in or going out, then we can write down that is equals to integration of rho A VA dot n cap. This n cap is nothing but surface normal of the region R, okay. So, rho A VA dot n cap into dA, okay. So, this we have got as net inflow or outflow, summation of net inflow or outflow or net efflux. Then let us say there is some sort of volumetric generation of species A also inside region R. This may happen whenever you are having chemical reaction, okay. So, this can be positive as well as negative, but here let us consider that volumetric generation we are having. If we are having volumetric absorption, then in that case it will be negative, okay. So, this is gamma A triple dashed we are taking as volumetric generation, okay. Then if we try to balance, then we can write down this this term, that means this mass of the species, change of the mass of the species, okay, which will be nothing but dMA dt, okay. So, if you try to do dMA dt is equals to whatever flux you are getting, okay, plus your whatever generation you are having over the whole volume, okay. So, this conservation of the species we can write down easily by taking arbitrary region R, okay. Next, once we have this arbitrary region R, then you can put this value of MA as we have derived in the last slide. So, ddt of MA will become, if we take the differentiation inside, so it will be del T of rho A into dV, and that is in having integration over the whole volume, okay. And in the right hand side we are having efflux and generation term respectively, okay. Then if you take all this term in one side and try to take derivative of the all terms, then you get this fashion, integration of V is into integration of over the whole domain, over whole volume, and then del T of rho A plus del dot rho A VA minus of gamma triple dashed A, and that is integrated over the whole volume V, okay. And now you see we have taken a arbitrary region R having volume V. So, this holds for any arbitrary region. So, we can say basically not this integration, the term whatever we are having inside, that is equals to 0. So, let us take this term is equals to 0, and here we have written the term for species A, as well as species A is very much generalized, we can take the similar equation for species B also, okay. So, we are having two species, let us say species A and species B, the conservation equation goes like this, okay. Then let us take two things over here. First one is, let us say it is only bicomponent mixture. So, whatever generation is there for species A and species B, their summation will be equals to 0. Why? Because in a overall system mass cannot be generated. So if this system is generating mass, A is generating mass, then definitely B will be destroying mass. Okay, so gamma A triple dash plus gamma B triple dash will be obviously equals to 0. And on the other hand, just now we have shown that density rho can be summation of rho different species rhos. So rho equals to rho A plus rho B, let us consider. Okay, so with this, if we add these two equations, then we can get the first term becomes del T of rho A plus rho B, which can be written as del T of rho. Second two terms summation becomes del of rho A V A plus rho V V B. Okay, so this once again can be written as rho V for the mixture, as we have shown over here. Rho V is equals to rho A V A plus rho V V V, okay, which is the mixture bulk velocity. So here this term, these two terms will be giving me del of rho into V, and the third two terms by virtue of this gamma A triple dash plus gamma B triple dash goes to 0. So for the mixture we get simple continuity equation in this fashion. Okay, so considering mixture as homogeneous, this equation we get. Okay. Next, let us go to Fick's law. This already we have shown that this is the derivation of Fick's law we have obtained. This was actually the mass flux J in the left hand side, and here we are having diffusivity and then the gradient of the concentration. Okay. So if we use this Fick's law part and try to have modification of this component del dot rho A V A. So let me show you how that is changing. Del dot rho A V A, let us try to write down as del dot rho A V plus del dot rho A V A minus V. So here you see this rho A V and rho A V is cancelling. So this term we have added and subtracted in this. So if you do so, here in this side we can actually replace it by Fick's law. So you see this rho A into V A minus V, over here it is coming. So we can write down this is nothing but actually minus rho dAB into del A. Okay, so that we have written over here minus rho dAB into del WA. Okay, so if you do so, then this second term of the species momentum equation we can write down in this fashion: del dot rho A into V minus of del dot rho dAB into del WA. Okay. Proceed further. If we proceed further, then you see the second term which was here, this term if we replace by this two terms, then this term can be taken in the right hand side. So we get the mass conservation equation for species A in this fashion. Okay. So this is the mass conservation equation for species A. Now let us consider, we know that rho A is nothing but rho into WA. This already in the first slide I have shown. So if you try to use that and make derivative with respect to T, then you get del rho A del T is equals to rho del omega A del T plus omega A you can keep fixed, and then del T of rho. So this is actually chain rule we are using over here for derivative. So this we will be replacing over here in the mass conservation equation. Okay. So and for the second term, you see for the second term we are having rho A into V. So rho A into V, that once again can be written easily as we know rho A is nothing but rho into WA, species concentration. So this we can write as rho A into V is equals to rho WA into V. Okay. And if we go for spatial derivative like this for the left hand side, then we are getting WA into del dot rho V plus rho V into del dot WA. Okay, once again chain rule we have used. Now let us put both this one and this del T of rho A over here in the mass conservation of species A, and then in the left hand side at least both the terms whenever we put, then we can see we are getting WA into del rho del T plus del dot rho V. Okay, so this from mixture momentum equation just now we have showed this is equals to 0. Okay, so this already we have showed over here, this is equals to 0. So we can reduce that part of the equation, this goes to 0. So in the left hand side we have only this term, okay, which is nothing but this can be written as rho into total derivative of omega. This is nothing but total derivative of omega. Okay. So once we incorporate this term over here in the mass conservation of species A, then finally we get rho into total derivative of omega is equals to del dot rho DAB into del WA plus gamma A triple dashed, okay, which is the generation. Okay. So, this is the species conservation equation for phase A. Next, let me show you some special case. If the constant density mixture we are having, then what we can do, we can consider rho as constant. So, in this equation, if we keep the rho constant, so this can come out, and DAB is always a constant. So, you can get the equation simplifies to rho and DAB came out. So, this simplifies to this form. Okay. And if you try to write down this total derivative in the form of del del t plus v dot del, then the equation goes like this. Okay. The equation goes like this, and you divide by rho, then the equation goes like this. Okay. Proceeding further, this WA is nothing but CA by C, okay, concentration of A by the overall concentration. Okay. So, many a times this overall concentration will be equals to 1, okay, for bicomponent mixture at least. Okay. So, here you will be finding out, if we put this omega WA is equals to CA by C over here in this equation. So, this whole equation is being converted to this form. Okay. So, del del T of CA plus V dot del CA is equals to DAB into delta square CA plus gamma A triple dashed, which is the generation part. Okay. So, we have observed constant mixture density special case, and then let us try to see during this type of diffusion how heat transfer is coming into picture. So, first I will be giving you one example where it is more or less similar to forced convection. So, let us say you are having a plate over this, okay, where the concentration of certain species is C, okay, and here we are having some inflow just similar to our flow over a flat plate. We are having some inflow having concentration C infinity. So, we are having a concentration gradient over here. So, just similar to your temperature profile, if you try to plot over here the concentration profile, so you will be getting adhered with the wall of the plate, you will be having high concentration, whereas in the free stream it is actually tending towards the C infinity, the free stream concentration. Okay. And similar to our thermal boundary layer, we can also consider a concentration boundary layer, which is nothing but where the concentration is reaching 99% of the free stream concentration C infinity. Okay. So, this type of concentration boundary layer can also be plotted analogous to your thermal boundary layer. Now, let me show you how concentration equation can be plotted. So, you see, if we consider that we are having from this equation, let us say consider we are having steady case. So, the first term drops down, the second term is actually giving you for 2-dimensional situation U into del C del x plus V into del C del y. Okay. And if we consider that there is no reaction, so this term will be going to 0. In the right hand side we are having DAB, and then if we neglect, just following our thermal boundary layer, if we neglect del square C del x square. Okay. So, this is x direction, this is y direction. So, if we neglect that term, then in the approximation of boundary layer, this becomes my concentration equation, along with the boundary conditions. Definitely at y equals to 0, C equals to C naught, and at y by delta naught tends to infinity. That means whenever we are going away from the plate, C becomes C infinity or the free stream concentration. So, this becomes my concentration equation, and these are the boundary condition. Okay. This is similar to your forced convection situation. If we proceed further and try to find out the mass transfer coefficient, just like our heat transfer coefficient. So, H in the heat transfer coefficient, it was Q by the temperature difference. Here it will be mass flux Jy and at wall definitely, okay, because we are interested in heat transfer coefficient, mass transfer coefficient at wall, and this is nothing but concentration gradient C naught minus C infinity. Okay. So, if you use our Fick's law, then this J can be written in this fashion, and finally this you see this omega can be converted to C, as we have shown in the previous few slides, the relationship between omega and C. So, ultimately the mass transfer coefficient comes out as this term. Okay. So, minus diffusivity into del C del y at y equals to 0, that means at wall divided by C naught minus C infinity, the concentration gradient, okay, concentration difference. Okay. Next, let us try to define local Sherwood number. This is analogous to your Nusselt number. So, if you try to define Nusselt number, that becomes Hx by k. Here it is nothing but H mass transfer into, this is actually mistake, so this is H mass transfer into x by dAB. Okay. So if you do that, then from, if you put this equation over here, then this Sherwood number becomes del C del y at y equals to 0 into x divided by C naught minus C infinity. Okay. If we try to find out heat transfer similarity, in heat transfer, convective heat transfer, we have shown Nusselt number will be nothing but Reynolds number to the power half and Prandtl number to the power n. So the value of n depends on the limits of Prandtl number, low Prandtl number limit and high Prandtl number limit. Here also we find out Sherwood number is nothing but A into Reynolds number to the power half, and the new number which is analogous to Prandtl number comes over here as Smith number. Okay, this is Smith number. Later on I will be telling you what is Smith number. We can write down this local Sherwood number in the function of Reynolds number and Smith number. Okay. So if you go for Reynolds analysis, then this Smith number can be written equals to 1. This is once again mistake, this is SC Smith number. Okay, concentration and temperature profile, then we will be looking analogous or same in case of Smith number equals to 1. Okay. Then let us see the another dimension, which is nothing but natural convection driven mass transfer. So let us have plate vertical like this. Now we are having gravity acting just in the downward direction, and here attached with the plate we are having high concentration C naught, and away from the plate we are having some infinitesimal concentration C infinity. Okay. So if you see like this, just like the temperature profile, so here it is TW, here it is T infinity, so temperature profile will be like this, our concentration profile will be also like this, and along with the temperature boundary thermal boundary layer, we can also have the concentration boundary layer. So this is your thermal boundary layer, and here we are having the concentration boundary layer. The concept remains same, 99% of the free stream concentration. Okay. So if we do like that, then we have to also see that how momentum equation is going to change, especially the buoyancy term, because this is natural convection. So buoyancy term, earlier what we have done using Bose-Einstein approximation, we have written rho equals to this first term only, where del rho del T came into picture. But here in this case we have to also see the del rho del C term, because concentration gradient is also coming into picture. Okay. So this term we need to add. Okay. Once we add this, and let us write down, earlier we know that beta is nothing but minus 1 by rho del T at constant pressure and concentration. Now let us define beta C. Okay. So beta C is for the concentration is equals to minus 1 by rho del C at constant temperature and pressure. If you do so, then these terms we can replace by beta and beta T. So let us do that. So rho equals to rho infinity minus of rho infinity beta T minus T infinity minus of rho infinity beta C over here. Okay, rho infinity into beta C minus C naught. Okay, so this pressure del rho del P we are neglecting. So if you do so, your buoyancy term will be having one extra term. Earlier we had only this is rho infinity into G, and we had this term which actually given rise to Rayleigh number. Now we are having another extra term due to the concentration difference C minus C infinity. Okay. And if you proceed further to the momentum equation, you see earlier the momentum equation was up to this, where buoyancy term has taken this form, okay, along with this one. Here the third term will be also present, okay. And if you proceed further, then you will be finding out this term will be prevailing like this, and subsequently here also in the boundary layer approximation, along with this G beta delta T, we will be having G beta C delta C also, okay. So these are the boundary layer equations where mass transfer and heat transfer present simultaneously, okay, continuity and momentum equation. And corresponding, obviously your energy equation will be remaining same, convection and conduction in 2D, and subsequently we have to also have the transport equation of species, which I can write down like this. Earlier also I have shown this equation for forced convection case, okay. So it will remain same. And if you see the boundary condition, this momentum equation and energy equation boundary condition already we have discussed. So for the concentration we will be having C equals to Cw at wall, okay, and C tends to C infinity away from the wall, okay. So, once you do these things, then you can easily solve natural convection thing. Now, let me show you what non-dimensional numbers are important for mass transfer. Already we know Prandtl number, which is nothing but nu by alpha. Okay. Similar to that, we will be also having Smith number, which is nothing but mu by rho dAB, where this dAB is nothing but the mass diffusivity, which I have introduced in this lecture. Okay. Then we will be having Lewis number. Lewis number is nothing but alpha by dAB. Alpha we know thermal diffusivity, dAB is the mass diffusivity. Okay. So, Lewis number gives you the relationship between the thermal and the mass transfer effects. Okay. Now, if you try to manipulate these three numbers, then you will be getting Smith number is equals to nothing but Prandtl number into Lewis number. So, Smith number is equals to PR into LE. Okay. On the other hand, if we try to see the heat transfer extent, so Rayleigh number was actually G beta delta T x cube by nu alpha. So, here we are having mass transfer Rayleigh number RAM. Okay. So, that will be G beta C. So, remember we have introduced beta C, and here in place of del T we will be having del C, and this alpha will be changing to your diffusivity. Thermal diffusivity will be changing to mass diffusivity. Okay. So, these new numbers we will be handling, and also we have seen that how Nusselt number analogous relationship we have got for Sherwood number. So, here Nusselt number relationship was for natural convection, it was in terms of Rayleigh number. Here it will be mass transfer Rayleigh number RAM, and Prandtl number will be transforming to Smith number. This is also SC, this is not SE. Okay. So, all these analogous things we have seen in this lecture. Let us summarize now. So, first what we have done in this lecture, we have stated the Fick's law. So, we have seen Fick's law comes out in this fashion. Then we have showed you the transport equation for individual species, and we have shown that transport equation of individual species goes like this, where diffusivity is over here, generation is over here, and this is the inertia term for the individual species. Okay. Then we have discussed about natural convection and forced convection driven mass transfers. Okay. So, two separate cases we have shown you. We have also defined non-dimensional numbers related to mass transfer, and finally established analogy between the mass transfer and convective heat transfer. Okay. So, with this I will be ending my lecture, but before leaving, let me test your understanding what you have understood in this lecture. We are having three questions. So, first question is mass diffusivity has unit as, so we are having meter per second square, meter square per second, and meter cube per second. So, it is very simple. In the first slide I have told you. So, obviously correct answer is meter square per second. Second question, Nusselt number of heat transfer is analogous to Smith number in mass transfer, Lewis number in mass transfer, Grashof number or Sherwood number. So, obviously you have understood, we have discussed so many times, Nusselt number is actually analogous to Sherwood number. So, this is the correct answer. Last, which relationship is correct? Okay. So, SC equals to PR into SH, Sherwood number, Smith number is equals to PR into Lewis number equals to Prandtl number into Sherwood number, and Smith number is equals to Prandtl number by Lewis number. So, obviously this also we have said that Smith number is equals to Prandtl number into Lewis number. This is the correct answer. Okay. So, with this I will be ending this lecture. In our last lecture we will be discussing about some problems on convection inside a duct, and as well as we will be discussing about mass transfer. Okay. So, if you are having any query, please do not forget to keep posting in our discussion forum. Thank you.